The future of space, colonizing Mars and the search for extraterrestrial life. The dream of a home on Mars and finding cosmic neighbors is becoming reality. Are you ready to look into humanity's near future in space? Since time immemorial, humans have been drawn to the night sky. This vast, shimmering world has always beckoned, sparking questions about our place in the universe. What are those stars? Are we alone? And the biggest question, what's beyond our little blue marble? This isn't just romance. It's a deep-seated instinct to explore that has driven humankind for millennia. First and foremost, we explore space out of pure scientific curiosity. We want to understand the universe's origins, how galaxies and stars form, and the laws governing this grand theater. Each mission, each orbiting telescope, is our eye peering into the past and into the fabric of space-time. This research expands our knowledge and sparks new technologies that improve our lives on Earth. Beyond the romance and science, there are more practical, even existential reasons. Earth is our only home, but it's finite and fragile. Resources are limited, and threats like climate change or asteroid impacts loom. Becoming a multi-planetary species isn't a luxury. It may be the only way to ensure humanity's long-term survival. Imagine asteroids rich in metals or lunar regolith containing valuable elements, becoming resources for future generations. Colonizing Mars, as we'll discuss, isn't just a pipe dream. It's a step towards creating a backup plan for civilization. It's an ambitious project requiring immense effort, innovation, and collaboration, but the potential payoff is immeasurable. It pushes us to solve complex engineering and biological problems, spurring progress across all fields of science and technology. Ultimately, the call of the stars isn't just about adventure. It reflects our need for growth, pushing boundaries, finding answers, and ensuring a future for those who come after us. We look to the sky not because it's easy, but because it's necessary. Do you know the incredible challenges of getting to Mars and how we plan to overcome them? The red planet, our nearest cosmic neighbor, has long symbolized humanity's next giant leap. Once the realm of science fiction, Mars is now the target of ambitious engineering projects by space agencies and private companies. What does colonization mean? And what challenges stand in the way of creating a new home in space? Let's start with current projects. NASA is developing the Artemis program, focused on the Moon, but part of a broader strategy for sending humans to Mars. But the loudest voice belongs to Elon Musk and SpaceX. Their goal is to build the Starship, a reusable transport system that can deliver hundreds of tons of cargo and dozens of people to Mars to create a self-sustaining colony. These are just study missions. They're plans to establish a permanent human presence. However, Mars isn't exactly hospitable. The technological and logistical challenges are monumental. First, the journey itself. The trip to Mars takes 6 to 9 months, meaning long-term exposure to microgravity and cosmic radiation. Developing effective protection and faster engines is crucial. Starship promises to cut travel time, but risks remain. Second, landing. Delivering heavy equipment needed for construction and life support is incredibly complex. Mars's thin atmosphere isn't sufficient for effective braking, requiring advanced parachute systems and engines. The amount of payload we can safely land determines what we can build. On the surface, conditions are harsh. Temperatures range from -220 degrees Fahrenheit at night to 70 degrees Fahrenheit during the day. The thin atmosphere offers little protection from radiation, making underground or shielded habitats essential. Plus, Mars is known for global dust storms that can last for months, blocking sunlight and threatening solar panels. Life support logistics are another challenge. How do we provide colonists with air, water, and food? This is where in situ resource utilization, ISRU, comes in. Mars has water ice, especially at the poles. We can extract oxygen from water for breathing and hydrogen for rocket fuel. Carbon dioxide from the atmosphere can also be used to produce methane, fuel for the return trip or for generating energy. Creating closed-loop ecosystems for growing food, recycling waste, and maintaining psychological well-being in isolation requires unprecedented innovation. Every detail must be carefully considered and tested. Colonizing Mars isn't just flying to another planet. It's creating a new civilization in extreme conditions. It's a challenge that forces us to develop new technologies, think bigger, and unite to achieve a truly grand goal. The first settlements will lay the foundation for humanity's future among the stars. This will change our understanding of life beyond Earth. On Mars, we'll learn not just to survive, but to create complete self-sufficient worlds under domes. So we've made it to Mars and faced its harsh realities. The key question is, how do we live here? Creating self-sufficient settlements isn't just building structures, it's building ecosystems capable of supporting human life in an alien environment. This requires both engineering genius and a deep understanding of biology and ecology. The first Martian habitats will likely be modular. Imagine inflatable domes delivered from Earth in compact form and then inflated on-site, creating airtight and spacious volumes. These domes can be covered with Martian regolith for added protection from radiation and micrometeorites. Eventually, with 3D printing technology, we can build permanent structures directly from local materials, using regolith as a building powder. The heart of any settlement is the life support systems. Air, water, food, all must be in a closed loop. Water can be extracted from ice, known to exist on Mars, especially underground and at the poles. Electrolysis can split water into oxygen for breathing and hydrogen for fuel. Carbon dioxide, abundant in the Martian atmosphere, can also be used to produce oxygen and methane. Energy is another critical element. Solar panels will be a primary source, but their efficiency is reduced by dust storms and greater distance from the sun. Therefore, small nuclear fission reactors are also being considered. They can provide stable and powerful electricity needed for complex industrial processes and life support. As for food, Martians won't be eating canned goods from Earth. Inside the domes, there will be hydroponic or aeroponic greenhouses, systems for growing plants without soil, where roots receive nutrients from a water or aerosol solution. This maximizes the use of water and energy and produces fresh fruits and vegetables needed for a healthy diet. And of course, the most ambitious dream, terraforming Mars. This is the hypothetical process of changing the planet to make it more Earth-like, with a dense atmosphere, liquid water on the surface, and even vegetation. This isn't a task for one generation. It's a project spanning centuries or millennia. Methods may include releasing carbon dioxide from the polar caps and underground reservoirs to create a greenhouse effect, using orbital mirrors to direct sunlight and introducing genetically modified microorganisms to change the soil and atmosphere. While terraforming remains science fiction, initial steps towards sustainable settlements are already laying the groundwork for such a future. Each dome, each life support system is a miniature model of how we can change an entire planet. It's an incredible challenge, requiring ingenuity and long-term vision. In August 1977, the Big Ear Radio Observatory picked up a 72-second signal, so powerful and unusual that astronomer Jerry Emin wrote "Wow" on the printout. Since then, this phenomenon remains one of the most mysterious chapters in the search for extraterrestrial intelligence. The WOW signal was just one bright but unsolved episode in the quest to find alien intelligence. Ever since humanity realized the immensity of the universe, the question, "Are we alone?" has haunted scientists. This search, known as SETI, Search for Extraterrestrial Intelligence, isn't just a scientific program. It's an existential journey that could change our understanding of ourselves and our place in the cosmos. The first systematic attempts began in 1960 with Project Ozma, led by Frank Drake. He also proposed the famous Drake equation. The Drake equation is a tool for structured thinking about the likelihood of intelligent life, considering the rate of star formation, the fraction of planets capable of supporting life, and the probability of developing a technological civilization. Each factor is debated, but its existence highlights the multifaceted nature of the problem. Modern SETI projects have greatly expanded capabilities. Instead of single radio telescopes, we now use arrays like the Allen Telescope Array. ATA, Project Breakthrough Listen, is one of the largest, using the world's biggest radio telescopes to scan billions of frequencies, covering millions of stars and hundreds of galaxies. We're not looking for random noise, but artificial, narrow-band signals that could be a targeted message. Despite all the efforts, we haven't received a confirmed signal. This leads us to the Fermi Paradox. In 1950, physicist Enrico Fermi, pondering the high probability of civilizations, asked, "Where is everyone?" Hypotheses abound. From the Great Filter, a barrier that life must overcome in the past or future, to the zoo hypothesis, where advanced civilizations avoid contact. Perhaps interstellar distances are too vast, or other civilizations use forms of communication we can't detect or understand. The search continues, and each new exoplanet, each new detection method brings us closer to solving this mystery. Whether it's a powerful signal or the realization of our loneliness, the answer will fundamentally change our worldview. Our role as explorers is to keep listening and searching, because somewhere out there, among the countless stars, the answer may be hidden. Did you know that beneath the icy crust of Jupiter's moon Europa, there may be twice as much liquid water as in all of Earth's oceans? And in our Milky Way galaxy alone, billions of planets are estimated to be potentially habitable. These staggering numbers point to incredible opportunities for finding life right now. Now that we've talked about searching for intelligent life, let's focus on a broader question. Where else can life exist in the universe, even in its simplest forms? The answers are closer and more diverse than we imagined decades ago. Our own cosmic backyard, the solar system, holds promising locations, not to mention the billions of exoplanets. Let's start with the giants of our solar system and their moons. Jupiter, king of planets, has an icy moon called Europa. Under its thick ice crust, data shows a vast ocean of liquid water, possibly twice the volume of Earth's oceans. This ocean is heated by tidal forces from Jupiter, creating potential hydrothermal vents on the ocean floor, similar to those that support life in Earth's depths. Missions like NASA's Europa Clipper are preparing to study this world, perhaps even flying through geysers, ejecting water into space. Imagine, beneath the ice, far from the sun, a whole ecosystem could exist. Another candidate is Enceladus, a small moon of Saturn. It also has a subsurface ocean, actively ejecting water and organic molecules into space through cracks in the icy surface. The Cassini spacecraft flew through these plumes and found hydrogen, methane, and carbon dioxide, key ingredients for life. It's practically a free sample of the ocean without drilling through the ice. Next is Titan, Saturn's largest moon. It's the only moon in the solar system with a dense atmosphere and stable liquid lakes and rivers on the surface. However, these lakes aren't water, but methane and ethane. Despite the extremely low temperatures, complex organic chemistry occurs here, which may be the basis for life unlike Earth's. But the real treasure trove for finding life is beyond our system: exoplanets. Since discovering the first exoplanet in the 1990s, their number has exceeded 5,000. Some are in the habitable zone, the range of distances from a star where liquid water can exist on the planet's surface. Some worlds, like the planets of the TRAPPIST-1 system, are rocky, Earth-sized bodies orbiting a red dwarf star. They have the potential to support life. New telescopes, like the James Webb Space Telescope, are analyzing exoplanet atmospheres, looking for biosignatures, molecules that indicate the presence of life, such as oxygen or methane in unusual concentrations. This is revolutionary and may give us the first direct evidence of extraterrestrial life. Searching for life isn't just searching for Earth twins. It's also expanding our understanding of what life can be. Maybe it's adapted to methane oceans, or subsurface seas, or atmospheres unlike ours. The possibilities are endless, and each new mission, each new discovery brings us closer to solving this cosmic mystery. We stand at the threshold of change, colonizing Mars and potential contact with extraterrestrial life. This isn't just scientific achievement. It's a moral and ethical challenge that will define humanity in the cosmic era. Are we ready for this responsibility? Space expansion, as inspiring as it is, carries ethical dilemmas. First is planetary protection. When we send spacecraft to Mars or other planets, there's a risk of introducing Earth's microorganisms, which could contaminate existing life or skew research. International protocols exist, but with growing private initiatives and ambitions for colonization, the issue of sterility and impact on other worlds becomes more pressing. Do we have the right to alter other planets' ecosystems, even if there's no intelligent life? Then there's the question of ownership and governance. If Mars is colonized, who owns its resources? What's the legal status of the first Martian settlements? Will they obey Earth laws or create their own? The history of colonization on Earth is full of conflicts and injustice, and we mustn't repeat those mistakes in space. Clear international agreements are needed to avoid a space race for resources and prevent conflicts. Another aspect is social justice. Who gets to go to Mars? Will it be a privilege for the few or available to all? How do we ensure equal opportunities and avoid creating a new space elite? These questions require serious consideration now. And the most exciting and worrying aspect, contact with extraterrestrial life. If we find even microbial life on Europa or Enceladus, what are our obligations? Should we study it, protect it, or leave it untouched? If we receive a signal from an intelligent civilization, should we answer? The dark forest theory warns that any civilization discovering another may be forced to destroy it to ensure its own safety. This scenario makes us think about the consequences of our first hello. The ethics of space expansion aren't just rules. They're a philosophy of our future as a spacefaring species. It requires technological progress and moral maturity. We must act responsibly, with respect for the potential life of other worlds, and with an awareness of our role as guardians of this unique existence we call humanity. Only then can we build a worthy cosmic future. We've just taken a journey into the future of space, to colonizing Mars and searching for extraterrestrial life. These questions shape our future. If you're inspired by the endless possibilities of the universe and want to explore the unknown, subscribe to Epoch Echoes and like this video to not miss exciting stories about humanity's future among the stars.